Now that we know how to use the method of increments to figure out the instantaneous rate of change of an object as it moves through space, we want to actually apply that to other things as well. So this can be really useful for things that have nothing to do with time and things that have nothing to do with position or an actual velocity, but you still want to find out how fast some quantity is changing with respect to some other quantity that you're keeping track of. So instead of using the s of t that we've been using, which is the position for a given value of time, we're going to use the more general notation that you're probably already familiar with for functions, y equals f of x. And that just allows us to apply that to any kind of situation, and we can kind of work with it abstractly without thinking about the physical situation of time and space and distance. So we're going to start using y equals f of x. The big mathy word that people use for instantaneous rate of change in this general setting is derivative. So from now on, I'm going to be using the word derivative of a function. All it means is the instantaneous rate of change of that function. So it's just a word that means the same thing. An interesting thing about calculus is that it was mostly developed by two different groups of people who used a little bit different notation. And the notation that they used has been passed down so that we now use both sets of notation. And so this gives us, it gives you a little extra notation to have to be familiar with. But it's also nice because sometimes one set of notation is more convenient and other times the other set of notation is more convenient. So you definitely want to learn these. So if we've got the function y equals f of x and we want to find the instantaneous rate of change of that function f with respect to that quantity, that variable x, that's the derivative. One set of notation, we'll write it as the derivative is f prime of x. It looks like f apostrophe x, and it's read f prime of x. Or if we want to focus on y instead of the f, then we would write the derivative is y prime. So y apostrophe, but it's read y prime. The other set of notation, I'll set up by saying that we're going to also change the notation for the increment h that we've been using. The increment h was just a change in time. It's the amount of time that went by. So people started using triangle, the Greek letter delta, for change in. So the change in time we'll write as delta t, or triangle t. And when we move to the more general setting, we'll write it as delta x. That just means change in x. So instead of h in our formula, we'll have change in x. That's the thing that we're going to let shrink down to 0 after we've found the average speed, the average rate of change. The derivative notation that uses, or that looks most like that notation, the delta x, it writes the derivative of y. So we're still y equals f of x. It writes the derivative of y as dy over dx. And if you want to focus on the name f for the function instead of the label y, then you would write it as df over dx. So just a couple of different sets of notation that you need to get used to. The verbiage that you need to know is derivative. All it means is instantaneous rate of change, which we know how to calculate using the method of increments.